Let's talk about some strategy for testing series. So, we've done a number of sections now where we've gotten a variety of different tests for testing infinite series for convergence or divergence. We have the divergence test actually too. So, how do we determine when we come across a series, how do we determine which of these tests we should apply? And so, here is just some general strategy on this video. And it'll give you a little bit of guidance, but it really comes from practice. The more you practice with infinite series, the more likely you're going to be to choose an effective test to go through it. And if the test you choose doesn't work, then you can go back and try a different test. So the first thing that we should do is we should take a quick limit of the terms. And that's because the divergence test tells us that if the limit of the terms in the series does not equal 0, then we are divergent. And that's a quick thing that we should always do, whether we do it in our heads or actually write something down. But we should always just test to make sure that the limit of the terms is approaching 0, because if it approaches 0, then this test is inconclusive and we move on. So let's just look at a quick example. So here is one, we've got a series. We've got 3n squared plus 2 over 5n squared plus 1. And a quick limit here will show that when we take the limit of these terms, 3n squared plus 2 over 5n squared plus 1, and that, of course, is infinity over infinity. But let's go ahead and do that 1 over n squared. We could look at the ratio of the lead coefficient, since that's also a rational function. But if we do it this way, this will be a quick and easy way to show that the limit here is 3 plus 2 over n squared and 5 plus 1 over n squared. When I distribute the 1 over n squared to the top and bottom, this becomes 3/5, which is clearly not 0. Therefore, this is divergent by the divergence test. And so that's a quick and easy look, a lot of times we can visually see if the limit is not going to be 0. If we can't see it visually, we run through the limit. But that's the first step. Take that quick first step of looking at the limit of the terms to see if you can apply that divergence test. Now, the next thing that we would want to consider if it is the series we're looking at is one of our special series. Is it one of our known series, one of our special series, useful series that we've worked with? And so, of course, the first one I have here is the P series. Is it a P series? Because we can determine from the size of the exponent greater than 1 or less than or equal to 1, we can determine convergence or divergence. Is it a geometric series? If it's a geometric series, we can determine by that common ratio, how that common ratio plays out relative in absolute value to 1. Or is it a telescoping series? Is it one that's going to collapse in upon itself in the partial sum? So here's some examples of some telescoping series. I'm not going to go through those. We've discussed telescoping series on a different video, but those are two telescoping series. And over here, I threw a couple of examples of P series or geometric series. And so here's some P series, and we can see, again, these are kind of our first couple of ideas because these are quick and easy to think about. I'm looking at this one, this is k to the 2/3, because I can quickly identify the powers and determine convergence or divergence. These are two geometric series, and I can quickly see from the common ratio that I've got convergence on the first one and divergence on the second one relative to how they relate to 1. So those are the first things that we want to think about when we're looking at a series. Run the limit of the terms themselves to make sure that we can't apply the divergence test. If we can, if that limit is not equal to 0, we get divergence right away. And then we check to see if we are one of our special series. If we're one of our special series, then we can apply our rules for the special series, the P series, the geometric series, or if it's a telescoping series, we can see how the partial sums telescope and then take the limit of the partial sums. Okay, so what if it's not one of our special series, like a P series or a geometric series, but it looks like a P series or a geometric series? Well, that's when we pull out that comparison test or limit comparison test, either the direct comparison test or the limit comparison test. So if we have a series that looks very similar to a P series or a geometric series, then we want to think about our comparison test, compare directly with an inequality, or or limit comparison test. So we can use either of those two. And here would be a couple of examples. So when I'm looking at a series of this form, when I come across a series here, the first thing I notice here in this series, I've got a lead power of k cubed on the top and a lead power or high power in the denominator of k to the fourth. And so I'm thinking to myself, I'm going to use one of my comparison tests, and I'm going to compare to k cubed over k to the fourth, which is 1 over k to the first, which diverges by p series. P equals 1. That's the harmonic series, actually. So P series P equals 1. And in this particular case, it is likely that I would use limit comparison. So I'm looking at this and I'm thinking, you know what? This looks like a limit comparison test here. Rather than trying to set up a direct inequality, I think I'm going to work with limit comparison test on that one. And then if I look at something like either of these two, here's two other examples. Similar to the previous one, I would look at the high power in the top here and the high power in the bottom here. And I'm thinking, you know what? I'm going to compare this guy to a series 4n to the fourth, take that high power there, and it's the square root of 3n to the 10th. Of course, the 4 and the root 3 are just constants, so I don't actually need those 4 and root 3. And I've got n to the fourth, and in the bottom, I have n to the fifth. And I can play that out. And again, think about that like a 4 root 3. That actually comes out as a constant. And I've got 1 over n to the first, and that's a p series where p is equal to 1 and we have divergence. And I'm thinking, you know what? I'm going to come back here and I'm probably, once again, going to use limit comparison test on that one. And on this guy, I see that negative 2 to the k and that 3 to the k. And I'm thinking to myself, you know what? That's looking like an awful lot like the geometric series 2 to the k over 3 to the k, which I know is 2/3 to the k, which has an r of 2/3, which of course in absolute value is less than 1, and so that converges by geometric series. And since that converges, I'm coming back to my original series here and thinking, you know what, I think I'm going to use some limit comparison. You know, on that one, I think we could actually even play around a little bit and use direct comparison. We might have to split it up, but I think we could even use direct comparison if we wanted to. So that's if we've got a series that looks like one of our useful series, but isn't quite a useful series. Under this same strategy of comparison, let's also talk about something where the terms are not always positive. Because remember, in the comparison test, we do have to have positive terms. And so if the terms themselves are positive and negative, or just in general, they have some kind of bounding or something of that nature, like in this case, I'm seeing that cosine of k. Anytime we have, another thing we could add here is anytime or bounding. Anytime we've got functions, remember that sine of n, or let's use k, sine of k is in between 1 and negative 1. Cosine of k is in between 1 and negative 1. Inverse tangent of k is between pi over 2 and negative pi over 2. So any of these, if we have bounding, like on this particular one, I look at this and I think, okay, well, in absolute value, 1 plus cosine of k over 5 to the k, in absolute value has to be less than or equal to 2 over 5 to the k, which is 2 times 1/5 to the k. And the series 2 times 1/5 to the k is a geometric series where r equals 1/5. This is geometric series and converges. So I can use some direct comparison here to show absolute convergence. So just another thing to mention here, if our terms are both positive and negative, or if we have any kind of bounding, comparison can be really useful in those two scenarios as well, because what we can do is we can look at the absolute value of the terms and then build an inequality where we can use direct comparison or even limit comparison test. Okay, so our big dogs here, the ratio and the root test. These are very powerful tests and often useful, sometimes even the first thing we might think about using. Now, I went through those other tests because some of those other tests are obvious upon inspection of the series. But if upon inspection we don't see any of those other tests, the comparison to our useful test or the actual useful, I'm sorry, our useful series or the actual useful series themselves, then we might get into the ratio and the root test. So if the series has factorials or constants raised to powers with an index, are the terms themselves in an expression that is raised to a power? Any of those sort of questions, if we can answer yes to any of those, might want to consider using the ratio or the root test. The other nice thing about the ratio and the root test is that it gives us, if the limit of the ratio or the root is less than 1, we get absolute convergence. And so it's a strong test, and it tests for that absolute convergence off the bat. And it doesn't matter if the terms have alternating signs or change signs. So here are some nice examples, and I won't go through these again. We spent a lot of time on the examples for the ratio and the root test, but here would be a nice one. On this one, I see that factorial, and I'm thinking, ratio test, and I would run that through the ratio test. This guy, I see that power to the k, and I'm thinking, ooh, this is a good one for root test, and I would run that through the root test. This one, I see both the power on k and the factorial, but because of the factorial is telling me I'm going to try the ratio test. I know with factorials, when I look at ratios, I get a lot of canceling. So that's a really nice test. Well, technically, it's two tests. That's a really nice test, and it gives us that absolute convergence or divergence. Now, if it happens to be inconclusive, we've got to run back and try something else. And that's where we might get back into looking at, after we take the absolute value, a comparison or one of the other tests. Okay, let's consider, or we might get into, if it's an alternating series and the ratio or the root test is inconclusive, this is where we might get into thinking about the conditional convergence through the alternating series test. So one thing to note, when we do the alternating series test, the first thing we always want to do when we're testing a series is we want to test the absolute value of the series. That will give us, if it's convergent in its absolute value, it gives us absolute convergence. But if its absolute value is divergent, that's really the only time we want to kind of get into our alternating series, because in our alternating series, we could get conditional convergence. So we'll take a look at those. If we've got a alternating series after being tested for absolute convergence, then we can get into looking at alternating series. So again, on both of these, I would first test in absolute value and see what happens in absolute value, and then if not, check with the negative there as well. Okay, let's talk about this last test that we haven't addressed yet, and that is the integral test. And even though it's one of the first ones that we learned, it is very specific, and now we have a load of other tests that we could apply that may give us convergence or divergence before we have to use the integral test. So that's why it's later in our list here of tests as we're running through some strategy. And so this again is very specific. If we happen to have a function that can model the terms of our series, and that function is eventually continuous, positive, and decreasing, and we can actually take the integral, right? It's very specific. We have to have all these conditions met. If we can take the integral, it's an improper integral because it's going to go to infinity, from n to infinity of that function, and we can determine if that integral is convergent or divergent, then of course the convergence or divergence of that integral through the integral test gives us the convergence or divergence of the series. So again, it's kind of specific, and we have to be able to integrate the function and have a function that models the terms of the series. But that said, if that's the case, then we can use the integral test. So here would be one that we might want to use the integral test on. This is one that the first thing, as mentioned before, the first thing we want to do though is we want to look at the absolute value, because obviously with that switch, this guy is not always positive. So the first thing we do is we look at the absolute value, and then that becomes the series 1 over k natural log of k, and that can be connected to the function 1 over x natural log of x, because if we plug in the integers, we get the terms of the series from k equals 2 to infinity. And then we can consider the integral from 2 to infinity of 1 over x natural log of x dx. Of course, that is an improper integral, so we're letting the we're going to put in t, it's kind of a dummy variable, t, we're going to let t go to infinity, and we're going to integrate from 2 to t of 1 over x natural log of x dx. And I'm going to leave that. I'm going to dot that out. We've done a lot of improper integrals. We've worked the integral test before. We're going to dot that out. We're going to say that equals, well, I don't know. We got to figure it out. Is that going to be convergent or divergent? Divergent. I'm running out of space at the bottom of the screen here. Is that convergent or divergent? We figure that out. If it's convergent or divergent, whichever one it is, that gives us the result and tells us that this series is convergent or divergent. If we had convergence, then our series we're looking at is absolutely convergent. If we had divergence, well, then we would come back to our series. That would mean the absolute value is divergent, but we still have that switch that we could address with the alternating series if we got divergence. So that's a nice one to kind of practice, and I will leave it there for you to practice on your own. And I will end here. If the test that we're looking at is inconclusive, if we run a test and the test is inconclusive, we do not get a result from whatever test that we ran. Guess what? We just got to go back and try something else. We got to pull another one of our series strategies, one of our series tests out of our toolbox, and we got to apply a different strategy if the test that we used was inconclusive. So don't give up, just go back and try something else. And on that note, the best way to practice testing series for convergence or divergence is to just test a bunch of series. So I have created this activity that I want you guys to work on together. So this activity is in the Canvas module. Go ahead, work all these problems on this activity. There are, I believe, let's see, I've got the pages here. I believe we've got 8 of them. So there's 8 problems for you to work and practice all your different strategies. Determine if, as you're doing these, determine if the series is absolutely convergent, conditionally convergent, or divergent, and show all of your work and justify each of your steps with the tests that you're applying. And then we have a discussion board this week where you get to share out your work and create a solution set for this activity with your group members. So please practice these, practice in the homework, practice these activities, and participate on the discussion board to get a really solid understanding of all of the tests that we use and how to apply the test and when to apply which test.